Today's topic is flow measurement and flow meters. As you can see on your screen, this is a typical gas pump, and we have all been to gas pumps multiple times to fill gas in our cars. Uh, but have you ever wondered how does a gas pump know how much gas it has pumped so that it can bill you accordingly? So the answer is basically it uses a flow meter which counts the number of gallons it passed through it, and then it keeps this count and produces the bill. Another application where we want to know how much fluid is passing per unit time is in various chemical plants where you want to precisely maintain the rate of chemical reactions so that uh, so then you need to pump the chemical uh, reactors, the reacting agents at fixed already known rates. And to do that, we must first be able to measure the flow rate. So this is where again various flow measurement principles are useful to calculate, to measure and calculate the flow rate accurately. So in this lecture, I'll be familiarizing you with different methods of flow measurement and different flow meters and their working principles. So this chart on your screen, it shows a classification of existing flow meters. Again, the flow can be in a closed pipeline or it can be an open channel flow. Let's say you're something like a ship cruising over water. That's kind of an open channel flow. And as you can see, there is a vast variety of these flow meters compared to something like pressure sensors or temperature meters. That's because uh, we have flow in various different situations, and the fluid can also be different. It can be liquid sometime, it can be air, uh, and we sometimes we also want to just measure the amount of fluid that is passing, that is how much volume or mass has passed, or sometimes we want to keep track of the flow rate, that is the amount of fluid passing per unit time. So for each of these applications we want to we basically have different techniques and different flow meters. So in this lecture you will basically get to know about these different flow meters and their advantages, disadvantages, and their range of applicability, so that if you want to measure flow in any of your applications, you would be able to decide which flow meter to use. So these flow meters are, I'll in this lecture I'll mainly concentrate on flow in closed pipelines, and again here also you want totalizers and total flow meters as something that you use in gas pumps or your household water meters. So totalizers mean that it just measures the amount of fluid that has passed. While on the other hand, the flow rate meters, they measure the uh, volume rate of flow, that is um, how much volume of fluid is passing per unit time, or it can even be mass. So if the fluid is incompressible, volumetric flow rate and the mass flow rate are related, you just multiply the volumetric flow rate by density, and you get the mass flow rate. So one kind of flow measurement is just the local velocity measurement of the fluid, and it can be done easily by using a pitot tube. You have already learned about pitot tube in your Bernoulli equation class. So the working principle of a pitot tube is um, very simple. There is an opening at the beginning as shown here, and I'll mark it as 1, and there are a bunch of holes on the side uh, which I'll mark with 2. So the point at 1 is just a stagnation point. So it measures the stagnation pressure in the fluid, while at point 2 the flow is passing over it. So point 2 just measures this static pressure. And using Bernoulli equation between point 1 and 2, we can then find out the velocity of the fluid from this pressure difference. So the velocity is simply square root of 2 times the pressure difference between the stagnation point 1 and the static point 2 divided by the density of the fluid. So this pitot tube can be easily used to measure the local fluid velocity. So let's say you have a laminar flow in a pipe as shown here, and then you just insert the pitot tube at different locations and you can find out the local velocity there. And as you know, in a turbulent pipe flow, the velocity profile is blunted, so you don't, so even if you measure it at different points, it will give you the same velocity. But this is particularly useful in a laminar flow where you have a velocity profile and the velocity of the flow changes different with its location in the pipe. And pitot tube is routinely used to measure the um, velocity of an aircraft or velocity of a ship. So again, it is attached to the head of the airplane and it measures the pressure at the stagnation point, and somewhere on the side of the tube, which is just a static pressure. And from this Bernoulli from this formula which we derived from the Bernoulli equation, we can find out the velocity of an aircraft. Similar principle can also be used to find velocity of a ship. So you will have to insert a pitot tube in the water like this. Now this was local flow measurement, but how does the gas pump or your household water meter count the gallons of fluid that has passed? So this is done by using something called direct measurements or positive displacement flow meters. Uh, so I'll first talk about direct measurements. Direct measurement is something like you just collect the fluid in a tank, and you can either weigh this fluid or you have markings for volume in the tank, and from there you can just find out how much of fluid is there. But this direct method is very manual and you cannot automate it. So and you cannot also use it in applications where you want a continuous flow and you don't want to disrupt the flow. So to get over this problem, we use something called positive displacement flow meters. So in these flow meters, there is a mechanical part which is either rotating or oscillating, and at one time it allows a fixed amount of fluid to pass through it. So let's say one rotation of this mechanical part is associated with a V volume of fluid. Then if you just count the number of rotations, you would count the volume of fluid that has passed. So the basic principle for positive displacement flow meters is that you trap a fixed amount of fluid and you count it. So these are basically typical geometries of these uh, devices which trap the fluid. So first one is here a Neutrating disc. So fluid comes in, and the geometry of this Neutrating disc is such that it traps a certain amount of fluid, and as this fluid flows from one side to the other side, it undergoes one complete rotation. So again, here you can just attach a gearbox at the top and you can count the number of rotations. Similarly, in a rotating lobe geometry, you trap the fluid which I have shaded here in blue, and as the lobe completes one rotation, this fluid, trapped fluid, goes from the upstream to the downstream. So let's say you again, the volume of the trapped fluid is V, and it does n number of rotations. So your total volume that passed is n times the volume of the trapped fluid. And again, the volume of the trapped fluid is designed by the manufacturers, and it is this information is provided when you buy the device. And similar principle is also applicable to your household water meters. So let's say the water comes in from this side, and then there is this notched gear in the middle with different sections, and each section here is associated with a volume, let's say V again. So as the fluid flows, then let's say if there are five such sections, so one rotation will lead to 5V volumes to pass through this water meter. And we can count the number of rotations by using this complicated gearbox, and then you know that it just gives the count on the scale which is attached at the top. So the basic principle here is that there is a fixed amount of fluid that the flow meter uh, allows to pass in one rotation or one oscillation, and we just measure the number of oscillations and get the amount of fluid that has passed. And these devices can only give us the amount of fluid that has passed. They cannot tell us about the flow rate of the fluid that is passing. Uh, so to measure the flow rate, we employ indirect methods. So we don't directly measure the volume and then divide it by time it required to pass that volume, uh, because that would be again very cumbersome to do. So one way to get around that is use obstructions in your pipe so that the velocity changes locally. And again, by applying Bernoulli equation, we know that if the pressure if the velocity decreases, then the pressure would increase, and then we just measure that pressure drop and relate it to the flow rate. So so these are called Bernoulli type devices because we are using Bernoulli's equation to relate the pressure drop to the velocity. And in these come in a variety of different designs, but three most popular designs are um, thin plate orifice, a flow nozzle, and a Venturi tube, and they are widely used in industry. So um, there is a vast amount of calibration curves and calibration data that can be used, and there are standard designs which are used across industries, so that finding out the um, information is very easy for these devices. So I'll explain in detail the design of all these devices and the working principle. So a orifice meter only has a simple plate which has a hole in the meter in the middle, and uh, it causes a contraction in the pipe. So you just install this um, orifice plate in a tube like this, and then as the flow comes in, it faces this obstruction, so it has to bend and so that it can pass through this small hole in the middle, and then again it goes out like this. So the disadvantage of this geometry is that since the fluid is suddenly contracting and suddenly expanding, the minor losses are huge here because there is something called vena contracta, that is the minimum area of the fluid flow occurs at some distance after the orifice plate, not exactly at the orifice plate, and um, that's because the fluid streamline cannot bend sharply, and it has to basically curve smoothly. So because of this, there is also a dead water region where the fluid is just circulating and it is not moving forward. This dead water region is also highlighted in this uh, uh, in this diagram on your left. Um, And because of this, the minor losses are huge. So to get rid of the vena contracta so that we can reduce the minor losses, we can use a flow nozzle. So in a flow nozzle, you have a streamlined contraction like this. So when the flow comes in, the streamlines can basically contract smoothly. But again, here, as the fluid comes out of this nozzle, it has to expand suddenly. So you basically prevent the vena contracta here. But again, because of this sudden expansion, there the dead water region is still present, and the loss and the head losses are again higher. But in a but a nozzle, a Venturi nozzle basically solves all this problem. It gets rid of the vena contracta, as well as it guides the fluid through a diffuser section so that it can expand smoothly. So the basic geometry is like you have a contraction initially, and then you have a diffuser section. So as the flow comes in, it can smoothly contract, and its velocity increases, and pressure drops, and then from this throat it can expand smoothly in this diffuser section. And because of this streamlined geometry, the losses are minimized. And in a Venturi nozzle, we also don't have any dead water region, so the minor losses are really very small compared to an orifice meter or a flow nozzle. So but the disadvantage of a Venturi meter is that its initial cost is very high, because it is a sophisticated design compared to the orifice or a flow nozzle. But the main advantage is that the losses are really low. So there is a trade-off here, and depending on what you are looking for, you might need to make a proper decision. So so the basic principle of all these three Bernoulli type devices is that we introduce an obstruction in the flow, so that the fluid velocity increases locally, and then because of this increase in the local velocity, we have a pressure drop, and we measure that pressure drop to find out the velocity. So let's say you have this kind of geometry where the upstream diameter of the pipe is d1. Then you have a throat which making the fluid to contract, and the size of this hole is small d, which is again some multiple beta of the upstream diameter, and this is also called the throat, because that is the minimum diameter in your pipe geometry. And then further downstream, we have a point 2 where we measure the downstream pressure. So we can measure this pressure by using a U2 manometer. So let's say the pressure upstream is P1 and the pressure measured downstream is P2, and this is the throat. So I can use conservation of mass first, because the same amount of fluid is passing. The mass flow rate is same at point 1 and at throat and at point 2. So rho times V1 times area at 1 is essentially equal to rho times V2 times area at 2. And we can also apply Bernoulli equation. So keep in mind the assumptions for Bernoulli equation. So we are assuming the fluid to be inviscid, incompressible, and we are applying the Bernoulli equation along a streamline shown here. And we are also assuming the flow to be irrotational. So the Bernoulli equation tells us that P1 plus half rho V1 square is equal to P2 plus half rho V2 square. So P1 V1 and P2 V2 are pressure and velocities at point 1 and point 2. So if we solve these two equations, we can find out the expression of velocity at 2 in terms of the pressure difference P1 minus P2, and it turns out to be equal to this formula as I written in the on the screen. So now that we know the velocity at point 2, we can find out the flow rate simply by multiplying it with the area. So the flow rate is basically A2 times V2, and this is an approximate flow rate because we are using Bernoulli equation, and we have used many assumptions like inviscid flow, uh, which are not exactly true. So this gives us an approximate value for the flow rate, which is just area times the velocity at point 2. But many times, like in a orifice plate, we do not know the area at point 2. That's because the fluid is contracting there. There might be vena contracta there. So the exact area at 2 is not known. But what is known to us is the exact area at the throat, because the diameter of the throat is a design parameter. So the diameter of the throat, small d, is known in terms of the upstream diameter, where here beta is just the ratio of small d1, and it is called the geometrical ratio. So that is known. So since A2 is unknown, we approximate A2 by a known area, which is the area at the throat, and then your flow rate is approximately equal to area at throat multiplied by this velocity term. So since we have used so many approximations to get the exact correct value of the flow rate, we need to correct this above expression for the flow rate by introducing a prefactor, pre-multiplier, which is called the discharge coefficient, and denoted by C subscript D. So the first expression is basically an approximate flow rate, but we have corrected it using this coefficient of discharge, and this is the exact flow rate now. Uh, and this coefficient of discharge is measured experimentally for each of the device by the manufacturer, and it is given in terms of uh, a chart or a curve fit to the experimental data. So this has been found to be a function of the upstream Reynolds number and the geometrical ratio beta. So once you fix the geometry, uh, then you can basically use these correlations given by your manufacturer to find out the coefficient of discharge, and then you measure the pressure difference and finally get the flow rate. So also the areas are basically related to simply to the diameters like this. So we can also replace the area in the above formula by their uh, forms in the diameters at those respective sections. So I can rewrite the flow rate as AD times the area in terms of diameter, and this term again. So this will be d raised to 4 upon d1 raised to 4, because area is area has a square uh, diameter term in it, and we know that small d by capital D1 is the geometrical ratio beta, and substituting it here gives us so this is the final form of the flow rate. And the way you basically find out the flow rate is that you first guess a Reynolds number downstream, and beta is known. So from this Reynolds number guess downstream and the geometrical ratio beta, you find out the coefficient of guess for the coefficient of discharge, and then you find out a guess flow rate using this CD and this complicated term in the square root. Now from this guessed flow rate, you can find out the velocity at the downstream by just dividing this with the area downstream. So this gives us a guess velocity downstream, and here you can again find out the Reynolds number downstream, which is basically rho times diameter and the guessed velocity. Now so the initial guessed Reynolds number was RED1, and the final answer is again this form for this Reynolds number. And if these two Reynolds number match, then that means your solution has converged and you have found out the correct flow rate. But if these Reynolds number don't match, then what you do is you modify your guess and then repeat this procedure again, and from the flow rate find out the Reynolds number again and see if they are matching. And you repeat this till you achieve convergence. And many a times computer programs are used for this iterative procedure, and they are also given with the device from the manufacturer. So since these are very popular and widely used designs, there are some industry standards so that we can make use of the already tabulated data for the coefficient of discharge. And some of these are given here. The first one is for a flow nozzle. Then you can see there is a standard for the shape of this curvature here and the length that should be used. Similarly, for an orifice plate, there are some standards for the angle that you use here, and for a Venturi flow nozzle as well, the half angle of the diffuser, um, and the and the and the place where you place your pressure taps is are have basically standard designs. Now, for these standard designs, the multiple experiments are already conducted, and from those experiments, manufacturers have found out the coefficient of discharge and how it depends on the geometrical ratio beta and the upstream Reynolds number. So let's say for a concentric orifice, the coefficient of discharge has this complicated form, which is found by basically curve fitting the experimental data, and this form is different depending on where we place our pressure taps in the orifice meter. So there are three standard places where we put the pressure taps. The first is corner taps. That just means you place the pressure taps adjacent to the orifice plate just before or after it. Other way can be D by 2 taps. So it means the upstream pressure tap is at a distance D behind the orifice plate, and the downstream tap is at a distance D by 2 in front of the orifice plate. And flange taps is taps means um, the pressure taps are uh, placed at a fixed distance, like one inch from the orifice plate. So for each of these pressure tap locations, you have different um, expressions for the coefficient of discharge. Similarly, for a long radius flow nozzle, the coefficient of discharge depends on the upstream Reynolds number and the geometrical ratio beta. So you can find out the coefficient of discharge for a long radius flow nozzle from here. Uh, Similarly, for a Venturi, the coefficient of discharge depends on the geometrical ratio beta, but it is found to be independent of the uh, Reynolds number if the Reynolds number is uh, very high and is in this range. So the procedure to find out the flow rate becomes very easy because it just depends on the geometrical ratio, and you don't need to basically follow the iterative procedure. Now again, as I discussed, all of these devices, because they are obstructing the flow, they lead to some non-recoverable losses, and one of that loss is just the major loss due to the viscous effects in the fluid, and which you can calculate by using Moody's chart. Another loss is basically the minor loss, which is because of the dead water region and the vena contracta. So as expected, the losses are, so this plot here gives the minor losses for orifice plate, flow nozzle, and a venturi, and as expected, the losses are maximum for an orifice plate meter compared to the flow nozzle and the venturi, because again I'll plot the flow from an orifice meter again. So the flow coming here, it basically cannot bend sharply, so it curves and it attains a minimum area in front, somewhere in front of the orifice meter, and we also have this circulating zone of fluid which basically leads to very high velocity gradients and high viscous stress. So because of this, the minor losses are the maximum in an orifice plate, but in a venturi nozzle, since we are guiding the flow as it contracts, the losses are somewhat minimized. But again, since the fluid as it comes out expands suddenly, the dead water regions are still present, and we have, because of that, we have some minor losses which are high, but they are lower than a thin orifice plate. And the losses are the minimum for a venturi because the design of venturi is such that the streamlines are never disturbed, and they basically they curve smoothly and diffuse out smoothly, and because of this, the vena contracta as well as the dead water recirculating regions are prevented, and the minor losses are minimum. The only loss here is basically the loss that can be calculated from Moody's chart, which is basically due to the viscous friction between the pipe wall and the fluid flowing because of the no slip boundary condition. Now these devices, these obstructive Bernoulli type devices are useful and are widely used, but as we have seen, they lead to significant head losses as the fluid flows, which is oftentimes is undesirable. So there are various other techniques as well, and I'll basically describe a few of those techniques which basically have uh, smaller losses, but they are also highly accurate, and in some of these techniques are also non-intrusive. So in these techniques, we don't need to disrupt the flow, we do not put anything in the flow, and we just install some sensor on the outer periphery of the pipe, and take measurements from outside. So the flow meters that I will discuss ahead are Turbine Meter, Vortex Meter, Ultrasonic Flow Meter, a Rotameter, Coriolis, mass flow meter and a laminar flow element. So this first picture here is of a turbine flow meter, and here the flow comes in the pipe, and we install turbine in this pipe, and as the flow hits the impeller blades of the turbine, this turbine rotates, and then we place a magnetic or electric pickup outside, so that as the impeller passes the magnetic pickup can record and count how many times the impeller is passing, and then we can relate the number of pulses per unit time uh, to the flow rate through the turbine meter, uh, and and this procedure is usually experimentally repeated for known flow rates for different fluids, so that we can come up with these calibration plots. And as you can see, the calibration plots are very different for different fluids. So whenever you are installing a turbine meter, you will have to calibrate it for 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 the fluid that you are going to use it for. So since there is no universal curve, uh, this 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 turbine meter is not that useful. Uh, the second diagram here is an ultrasonic flow meter. So the basic principle is that we send ultrasonic sound pulses from two sensors. One is installed upstream and one is installed downstream, and the signal that the upstream sensor is sending, it travels faster because going uh, it is traveling downstream, while the signal that the downstream sensor sends, it it travels slowly because it is going against the flow. So if we just measure the frequencies of these signals, and then their difference can be related to the velocity of the fluid flow, and this velocity then basically gives us the flow rate by if we multiply it by the pipe area. So that's the simple principle, and again, this is a non-intrusive method of measurement. We do not obstruct the flow, we just need to install these sensors outside, so the losses are really negligible here. Another principle is basically uh, the use of vortex shading around the bluff bodies, and this is called the vortex meter, which uses this principle. So as you might know, if we have a bluff body in a fluid, then the boundary layer on its surface separates after a while, and because of that we have wake behind the bluff body, and in this wake there are uh, vortices, and these vortices are periodically shed as shown on the screen. So there is something called a Strohal number, which is a non-dimensional number, which basically relates the velocity of the flow to the frequency of shading of these vortices, and the length scale of the object. So if we fix the Strohal number, then just by measuring the frequency of this vortex shading, we can find out the velocity of the flow, and this way we can find out the flow rate. So to measure the frequency of this vortex shading, we might use a pressure sensor, so that the pressure fluctuates, and we measure the frequency of these fluctuations, and this gives us the frequency of vortex shading. Here on the screen you can see a Coriolis flow meter, and the Coriolis flow meter is based on the Coriolis force, which an object experiences when it is moving in a rotating frame of reference. So the Coriolis force is given by mass times the Coriolis term. So the Coriolis term is basically 2 times the cross product of the velocity of rotation of the frame, of the rotating frame, and v is the velocity of the object, which is moving in that rotating frame of reference. So the way this principle is used to measure fluid flow is such that the flow is passed through a U-shaped tube, and this tube is made to oscillate in the middle as shown. So as the tube oscillates, the fluid that is coming in, it exerts a force on this pipe in a downward direction, while the fluid that is going out, it exerts a Coriolis force on the tube in the upward direction. And because of this, as you can see, the tube uh, twists, and we can basically measure this twist angle and relate it to the flow rate. The way Coriolis meter is implemented, however, is using two tubes, so that this twist is eliminated, and again we basically oscillate the two tubes in the middle by using a driver unit with a known frequency. So because of the Coriolis force, the signal that the sensor at the inlet uh, measures differs from the signal that the sensor at the outlet measures. So let's say we are driving the unit with a sinusoidal wave like this, then this is the signal from the driver unit. Then the signal that the sensor at the inlet measures, it lags behind this original signal like this. And the signal that the outlet measures, it is shifted to the right as shown here. So as you can see, there is a time lag delta t between the inlet signal and the outlet signal, and we can find out the mass flow rate through the pipe by using this lag in the two signals. And k here is just a coefficient which depends on the stiffness of the pipe and the geometry of the device. And also the frequency of these oscillations, it can be related to the density. So we can also measure density of the fluid using this formula, simple formula. So here m tube is the mass of the tube and v is the total volume of the tube. So once we know the mass flow rate and the density, the volumetric flow rate is simply mass flow rate divided by the density. So as you can see, Coriolis flow meter is also very versatile because it is giving us the mass flow rate as well as the density. Another device to measure flow is something called a rotameter. So in this device we have a vertical tube which has a tapered cross section. So its area is not a constant, but it changes with its height, and there is an object floating in this tapered tube. So as the fluid flows past this object, uh, there are three forces acting on this object. One is its own weight, the other is the force of buoyancy due to the fluid, and the third is the viscous drag as the fluid is passing past it. So depending on the force balance and the flow rate in the pipe, this object settles at different height. So if we change the flow rate, it it settles at a different height, and we can measure this height where it settles, and we can relate it to the flow rate. So flow rate is basically linearly related to the height at which this object settles via a, a constant of proportionality c, and this is again experimentally determined by the manufacturer, and the relation between the flow rate and the height is often given by the manufacturers, and in some cases along with the height, the flow rate is also a scale for the flow rate is also given along with the height scale. So I will not derive the equations in detail, but the basic force balance on this object is its weight, the force of buoyancy, and the drag force. So the force balance gives us that the drag is equal to the net weight of the fluid, which is its actual weight minus the force of buoyancy. The flow rate is equal to coefficient of drag times the weighted area of the float times 2W net divided by area of the float times the density of the fluid square root. So coefficient of drag um, is again determined experimentally, and this weighted area, it basically changes with the height, and it is the tube is designed in such a way that this weighted area a subscript a is a linear function of the height h. So then from here we can find out this constant of proportionality c, and we get the basically the flow rate. And in most of the flow meters, the flow is usually turbulent, so the velocity profile is kind of blunted and it is uniform because the various mixing that goes on in a turbulent flow. So in all these cases, we found out that the flow rate is related to the square root of pressure difference. So this is not a linear relationship, and let's say um, your flow rate reduces by um, 2 times, that means your pressure difference would reduce by 4 times. And if your flow rate reduces to a very small value, then your pressure difference will reduce even further, and sometimes measuring that small pressure difference is not possible, and it leads to many errors. So it is desirable that a different relationship, like a linear relationship between the flow rate and the pressure uh, is used. So that is possible in a laminar flow, because in a laminar pipe flow the velocity profile is not blunted but it is parabolic, and by solving Navier-Stokes equations we can basically find that the flow rate in a laminar flow is linearly related to the pressure difference. So let's say in a tube we have a tube of length L, and you are applying a pressure difference delta pre across this length L, then the flow rate is uh, given by this formula. So R is basically the radius of the tube. So as you can see, this is a linear relation, and it is more sensitive uh, to pressure, and we can also find out the flow rate accurately for even smaller pressure differences. So the way we use this is, since we usually have a turbulent flow, we install an array of uh, small tubes which have small diameter. So as you might know, the transition from laminar to turbulent flow depends on the Reynolds number, which is rho times velocity times length scale divided by the dynamic viscosity. So if we reduce the diameter through which the flow is passing, we ultimately reduce the Reynolds number, and if the Reynolds number is smaller than, let's say, 2300, then we have a laminar flow. So that's what exactly is done here. We have a very big diameter, let's say D1 upstream, but since we are installing this array of tubes, the diameter of each tube is very small and the effective Reynolds number then decreases, and hence the flow in these tubes is laminar. And then we can just measure the pressure gradient at the start and the end of these tubes, and let's say it is given by delta P, and we can then relate the pressure gradient to the flow rate by this simple linear relationship. Yes, so that 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 are all the flow meters that I wanted to cover in this lecture. And as you can see, there are, for depending on application and depending on the characteristics of the fluid, we have different techniques and different principles and different devices to measure the flow. So depending on their advantage and disadvantages, you can use um, a flow meter which suits your application. So that's it for this lecture. Thank you.